all are linear. The solution we got is u is equals to this is what we have got. It's a linear form. However, if second case, if a case is there where it is d by dx of e of x, e of x du by dx plus p of x. If this form is there, analytical solution is not guaranteed. So what we said was, if you look at the solution, this is u of x. Analytical solution cannot be some weird form from 0 to L. Then depending upon one element solution is like drawing a straight line between the, this is a one element solution, this is a straight line, whereas two element solution will be let's say the midpoint is somewhere here. The two element solution would be something like this, whereas many element solution would look something like this. And with the increasing number of elements, so this is for one element solution, this is two element solution, and third one 1 2 3 4 5 6 7 8 9 10 11, something around like 11 element solution would follow closely, something like this, 11 element solution. As the n increases, one can see that it will matches with the things. So we are talking about the convergence. These are H convergence, and what we said was, when you are picking the basis of an interpolation function, when of the shape functions which of the element to develop a shape function, which is like u tilde of x is equals to capital X times a naught a1, the best choice would be 1x. This is the best rather than taking x to the power of 7 or x to the power of 10, something like that. This is a wrong choice. This is a good choice, because when you are picking a complete basis, it is always best to take it in the powers of x to the power of 0, x to the power of 1, x to the power of 2, something like this in the increasing order. You take it. By doing that, your error, which is defined by the difference between your exact solution and your approximate solution, will only be order of h to the power of p, and p is the highest, is the next higher, is the 1 plus of the highest power that you have left it out in this place. Or an alternate way of saying is, it is the lowest power of the polynomial which was remaining after your interpolation function is defined. That means if I define it with respect to x to the power of 7 and x to the power of 10 in my thing, then if I subtract, let me call it as this as a universal set, and let's this call it as my basis set. So the P is defined as the minimum power of the set universal set minus B. So if B is x to the power of 7 and x to the power of 10, then you know that 7 and 10 is gone, still the lowest is x to the power of 0. That will be doing it. If I take something here, this one, x to the power of 0 and x to the power of 1 is taken, the minimum would be x to the power of 2. So the P would be 2 in this thing. So P is defined as the minimum power that is left it out after you are removing the basis function from the universal set. So it is always better to have this power as high as possible. That is only guaranteed if you make it, if the choice of the polynomial you make it in the trial function has all the least powers in it. Okay, so with that as a thing, I would say this completes your H convergence requirements. The other type of convergence is the P convergence. Okay, so today's class we will discuss little bit about the P convergence, and once the P convergence is there, I will again give you a detailed example of 1D bar element and development of the shape functions of the shape functions. So first thing, we have so far studied about two-noded bar. The two-noded bar would be node A, node B. Instead of a two-noded bar, if I take three-noded bar, then I will have three nodes. Similarly, I can as well as take, for example, four-noded bar. A four-noded bar so in the all the three example, case 1, case 2, case 3, your interpolation function would be, in this case, a naught plus a1x. Whereas in the second case, it will be a naught plus a1x plus a2x square. Here error would be order of h square. Here error would be of the order of h cube, because you have chosen x to the power of 0, x to the power of 1, x to the power of 2. Out of the universal set, the next thing, the next lowest power is x to the power of 3. So the P is 3 here. Similarly, in the third case, u tilde of x is given as a naught plus a1x plus a2x square plus a3 x cube. So that makes e to the power of x, so ex is of the order of h to the power of 4. So if you look at all the three examples, if you see that, let's say if suppose I refine the mesh by h is equals to h by 2. If I put it in this manner, then what happens is the error in the first case, since it is h square, the error would shrink for the new things as that is equals to its order of 1/4. Similarly here, E of x would reduce of order of 1 by 2 cube, which is 8. 1 by 2 cube, which is 8. Similarly, the error would decrease or diminish with a multiplier 1 to the power of 16. Similarly, if I take h is equals to h by 3, my error would diminish in the order of 1 by 9. My error would decrease in the order of 1 by 27. My error would decrease in the order of 1 by 81. So that means it is still one element solutions. Uh, it's still, if you look at it, the difference is with the increase in the number of nodes. If you clearly see, with the increase in the number of nodes, the p in this case was 2, the p in this case is 3, the p in this case is equals to 4. Okay, so if you are keep on increasing your p, then you are interpolating the same function using a higher degree polynomial. Here it is a linear polynomial, here it is a quadratic polynomial, here it is cubic polynomial. However, you need to understand that these are also complete polynomials. That's the reason p is equals to 2 is guaranteed. Instead, if I take a naught x to the power of 7, a1 x to the power of 14, I'm not guaranteed a complete polynomial. So you need to understand that if you take a complete polynomial, which is true for all these cases because all the lower degree powers are retained, like x to the power of 0 and x to the power of 1 here, x to the power of 0, x to the power of 1 and x to the power of 2. So whatever the highest or the what is the lowest power of p that is remaining in the universal, after taking their corresponding interpolation functions, trial functions, it will give you p is equals to 2, p is equals to 3 and p is equals to 4. So this, if you keep on increasing p, that is called p convergence, because you're using a better and a higher degree polynomial to interpolate the things. That means if I go back to the same solution here, let me redraw it. So let me take here, let's assume our solution is of this form. Okay, so if it is of this form, if I'm using only one element, if I'm only using one element in this, then one element is nothing but one element of, let me rewrite it as 1, 2, one element of two noded bar. Then I have two node, this is A and this is B. The solution is I can fit a straight line, so it's a linear curve. It's a linear curve. Now similarly, if I use still one element of three noded bar, a three noded bar is still you have a node here, you have a node here. Let's say the mid node is here. Then your solution, this is still a one element solution, but your approximation for this case is something like this. Now if I take one element of four noded bar, let's say I have the nodes at 1, 2, 3 and 4, my approximation would be, it's a cubic polynomial. So these are, the first one is a straight line, this is cubic curve. This one is a quadratic whereas the only two noded is linear curve. So it is still within this bar. If you have this bar, it is still a bar with one single element. Only one element is there, but in the first case, this entire element had only two nodes. Whereas in this case, let me draw it. For the first case, it is one noded bar. For the second case, for the second case, it was one node here, another node here, the third node was somewhere in between. So it is still a one noded, still a one element, but nodes are in this form. Now, for the third configuration, it is still one element, which is one node is here, another node is here, another node is here, and the fourth node is here. So if you look at the things, these two nodes are common for all the three, however, the other nodes are varying. So with the higher number of nodes, you have higher number of coefficient. If you have higher number of coefficient, the unique curve would be a higher degree polynomial. So in the first case, it is two noded. Second case is three noded, and the third case is four noded kind of a bar. And accordingly, the power, if you have n number of nodes, let's say if you have n noded bar, we can construct an n minus 1 complete polynomial based approximation. Based on this, our error would decrease as h to the power of n. Okay, so that's the reason even with the increasing number of the choice of bar, you can achieve the convergence. We, as I described in the previous class, e of x should vary as order of h to the power of p, which is nothing but some constant times h to the power of p. This is called your rate of convergence, and this is your degree of order or degree of convergence. So you can increase this p by choosing a higher number of noded element. So that is called p convergence. So either using h convergence or by p convergence, one can obtain a closer approximation to your exact solutions. At this point, I also would like to say that to review back again, to get converged solution, to summarize, first thing is increase number of elements. If you increase the number of elements, this is also called as H convergence. Let's say, for example, if you have a entire bar as one single element, if you make it the size of the mesh half, that means now you have two elements. If you make 1/3, your number of elements would be 3. If you make 1 by nth, number of elements is n. In that manner, if you are increasing the number of elements, the mesh size decreases. And if the mesh size decreases, even though the p is kept constant, here, even though this p is kept constant, so you can you can diminish this number as small as possible. That is one thing. The second thing is increase the number of nodes per element. That is nothing but P convergence. In the P convergence, you are keeping H constant. The size of the element remains same, but the order of the polynomial keeps on increasing. So that's the reason, or the degree of the polynomial keeps increasing. So if you look back here, see h to the power of p, h is kept constant, but p you are keep on increasing. Since hs is small, so what happens is you will make your error diminish as quickly as possible. So these two are the ways people generally try to attain the convergence. But there are also hybrid methods that's called as HP convergence, where people both use higher order polynomial for P and also a smaller size of the mesh, which is H. So HP convergence is also there. There are three types of convergence. So the crux of it is, if you keep on increasing the size, it will be H convergence. If you increase the number of nodes per element, it is P convergence. If you do both, it will give rise to HP convergence. So with this as the preset, um, which we have learned from the previous class, I'll close the convergence topic at this with this topic, and I want to re-summarize the entire unit 2 using two things today. The first one is, as I promised, today's class what I will discuss is obtaining stiffness matrix for the bar element. This is one thing. And secondly, um, after this is being done, I will give a detailed explanation of assembly, because that is a difficult topic which I felt yesterday there might be some confusion for you to understand. So I'll talk about an active live example um, involving assembly of stiffness matrix. So before I move into these two topics, let me stop here and ask for a couple of questions from your side. So the bar, which is, let's assume that this bar is non-prismatic. That means its cross section can also change. And let's say the stiffness is also changing, like a tooth. The outside enamel is hard and inside the soft tissue is soft. So E is also a function of X, maybe changing from one place to other place. Then we know and let's say it is also loaded with a kind of point loads as well as with some body forces inside small p. Then our governing differential equation, which we have discussed earlier, would come to be of this form: Ax Ex du dx plus p of x is equals to 0. Okay, so for simplicity, I'll rewrite this one by dropping the function of x as ae du dx for simple representation plus p is equals to 0. Now let's use the same method of weighted residual. Let's say instead of u, I am approximating u with respect to u tilde plus I have some error. So if I take this fellow and substitute in this, I know that d by dx a e du, this is not u but it is tilde of x dx plus p is equals to 0. So not 0. This is not 0. It will leave a residue, right? Because this is not u, it is only u tilde. Okay. So then we'll make use of our first chapter method of weighted residual. So what I do is I take this thing integration of r x and multiply with a weight v, which is maybe also function of x dx, integrated from the 0 to the length of the element. So what I'm saying is my weight, my residue, when multiplied with corresponding weight and I integrate this residue over the length, I want that cumulative weighted residue after substituting u tilde to be equal to 0. This is what is my condition. Okay. So making use of this, what I will say is, let's assume our u tilde to be x times a, or you can even write it as n times nodal values, where n would be x into A inverse, which we also discussed earlier. So this formulation is valid for all the cases. So now if this is u tilde, let's calculate strain. Strain is nothing but du tilde by dx. The du tilde by dx is nothing but, or you can write this one also as ni ui summation of I from 1 to small n, where n is the number of nodes per element. Now, if I take this thing and put it back here, now what I will get is, since n's are functions of x's, I can write it as, and ui's are nothing but simple arbitrary constants, I can write it as summation d by dx I is equals to 1 to n ni ui. That is nothing but ui d ni dx summation, because these are arbitrary constants. These are arbitrary constants and should be independent of x, whereas the only x functional, the independent variable dependence comes from the interpolation functions. This is how you can write it. Okay, so this makes our definition of strain. Now what is the definition? This is fine enough. I don't need definition of stress. Even you can get the definition of stress by multiplying it. Let's come back to this equation. See, your strain is nothing but the same as this one, so we are in the same form, we are in a better shape. Now let me rewrite this, let me rewrite this fellow by expanding here. So integral v, I'm removing that functional dependence of x, which is still there, but just for simplicity's sake I am removing it, d by dx ae du tilde dx now. When I expand this thing, The first term is this one, the second term is this one. Together has to be equals to 0. Okay. Now here use integration by parts. If you are using integration by parts, then I can rewrite it as dv by dx with a minus of ae du tilde by dx plus v ae du tilde by dx substituted at 0 and L plus the third term 0 to L p v dx. Now if you look at it, these things is nothing but the upper and lower limit will give us the boundary conditions. Okay, so that means our boundary conditions is nothing but either displacement constraints or the point loads. Those two can be accounted from this. And here at this point of time, I want to digress a little bit and want to give you a parallel analogy, which I might have given you a long time back in one of the previous lectures. When I was telling you about method of weighted residual, I have told you these things. Let me repeat it. Now, what are the characteristics of this V? What is V? What is V? V is a weight. By method of weighted residual, V is weight. How do you choose your weight? That is the question. How do you choose V? Choosing V is very similar to choosing the best friend. Okay. How do you choose your best friend? You don't pick anybody and say that he is your best friend. You choose your best friend by saying that if you like to go to a horror movie, your best friend should watch the horror movie. Then only you can gel with each other. Okay. If you hang out at a cricket match, you should also hang out at the cricket match. You like football or he likes a cricket match, then you cannot gel with each other. So that means you should be alike with your friend. And that is one thing. And I already said another thing is when we were kids in college, in early life, we used to celebrate birthday just like you guys. And in that, we used to get birthday bumps. And if your age is, let's say, some X number, you'll get X integers of beatings on your bumps. But there is one clause, you can transfer this thing, half of the beatings, to your best friend. And the best friend is really has to be a best friend. You cannot pick your enemy and say that this guy, half the beating can be given to the best friend. Okay. So there is consequence for that. So what are the consequences? If you pick an enemy, he will give you back beating later those things. So that's the reason we pick a best friend. Here also there is a reason for such kind of things. So what you need to do is pick your best friend. So here, how do you pick those things is, if, how do you pick is, this is the criterion. If at this point, let me rewrite it. How to pick V. So for that, let's answer the question, what is the highest continuity requirement of U? Here in this case, because of the bar, the highest is, let's see, for a bar, U has to be continuous, du by dx has to be continuous, d square u by dx square has to be continuous. If you find all these three, then only you can get your solution. That is, the continuity requirement for U is C2. C2 means this, if U is continuous, it is C0. If U and du by dx is continuous, it is called C1. If U du by dx and d square u by dx, it is called C2 and higher. But C2 is sufficient enough in your case here for that. But what we are doing is a finite element approximation. In the finite element approximation, we don't need to go up to C2 requirement. Just like the other day I said, if I want to buy a car, I don't need to have a 10 lakhs at my hand. I can have some amount and the rest of the amount can be taken loan. Same thing in finite element, what we say that my U tilde, this is the requirement of U. The U has to belong to C2. That's what the solution says. But what FEM says is U tilde is an approximation to U and this need not be C2. Then what it has to be? U tilde should belong to half of it. What is the half of this? Half. So this is good enough. So U tilde belonging to C1 is good enough. So this is one thing. Then who takes the other beating? The other beating will be taken by V. V should take the remaining part. V should also be C1. Okay. So if you start something, your friend should able to finish it. That's the reason we should choose the guy who is going to take the half load from you. So the V, the weight has to be complementing the remaining part of it, which you left out. Okay. So V should be C1. Is this just enough? No. Because we are integrating it. So if V belongs to C1, these two says that U tilde is continuous, du tilde by dx is continuous. And this one says that V is continuous, dv by dx is continuous. But just being continuous is not enough. Let's say if at one place it goes to infinity, then integrating it becomes difficult. So why? Because here if you look at this statement, you have dv by dx, ae, du by dx. This should not go to infinity, this should abruptly goes to infinity. So anything of this sort would lead to problems that this integral becomes, if there are any singularities in these two, this will lead to infinity, and if it leads to infinity, then it is of no use. It has to be finite. If it has to be finite, then any function f of x dx, if it has to be less than infinity, then this f belongs to Hilbert space. If this is true, this is h to the power of 0. But if any function f dash x dx should also be integrable, then f will belong to h1. So by this as the Hilbert space definition, we can say that in this expression, both du dx is there, dv by dx is there. And this integral has to be still finite. If it is infinite, then we are not in a good position to get the solution. So that means your V has to belong to H1 and U tilde should also belongs to H1. Okay, that is good. So that means this says that both some constant times u dx, sorry, v dx is less than infinity, and some constant times dv by dx when you integrate should also be less than infinity. This is h0, this is h1. This is true. Okay, as I said, again, we'll go back to parallel analogy. Your friend is taking half the beatings from you, but the birthday is yours. Okay, let's say birthday is yours, but your friend takes half the beating. At the end of the birthday, you'll also get a lot of presents. But we people are selfish people. So what we do is we never share our birthday gift with the friends. We want to share our beatings with the friend, but not the gifts. So you should pick a friend who is not jealous enough to take your presents, right? So that's the reason he should be your best friend. An evil person or an enemy person will never be so selfless in the friendship. He will always want something out of the friendship. Friendship itself means you should not expect anything. So that's the reason your friend V should not take your birthday gifts. Where is the birthday gift coming in this equation? So this is the place. So wherever du tilde by dx is specified, it is not a problem. You can just define it. That means wherever force boundary conditions are specified, it's okay. There is no problem. But displacement boundary conditions are specified, then this V fellow, what should this V fellow should take its value? So then it becomes nuisance. So, but if you make him the best friend, this V will take 0 when U is specified. That means there is another 0 to this guy at the bottom. That means this 0 says that wherever U is specified, V should be always equals to 0. Nothing. There is nothing else it can take. If U is delta, then V should also V should be equals to 0. If U is equals to alpha, it has to be 0. So no matter what value you specify at the boundary, that means you still have to do it. For example, let's see in our case. For this case, U is equals to at 0, it is equals to 0. So what is V at this place? It has to be 0. Let's say instead of a fixed support here, I have a spring support here. That means it is there on a spring support. And the springs are constrained here. This is spring support. And then this is your bar standing on it. Based on this push, because this is elastic foundation, this spring support is nothing but you go jump on your mattress in your home, you will see that with each jump you will see a spring action. So that end of the, let's say where your legs are supported, it is not fixed, but it is a spring support. The same thing, you jump on the floor will never, or even it does, but it is very small that you cannot differentiate that thing that is like very similar to fixed support. Here U is equals to some delta at this place, U of 0, but at that place V is still 0. This is what is your best friend. So no matter what you specify, either 0 or something, at the known or the specified values of V has to always equals to 0. That makes it, your definition of a best friend is not any random function, but it has to be this one. If U tilde is H1, your V has to be H1 0. Similarly for beam, this is for the bar. For beam, V tilde should be belongs to H2 0 and W tilde will belong to H2, because there you have fourth order differential equation. If this is 4, half is taken by this W and other half is taken by V. And it should also have this 0 criteria. That means it is selfless. By taking such kind of things, what will happen is there becomes a magic. Now, again, I will take this equation and rewrite it. Du tilde by dx plus v ae du dx specified at L minus v ae du dx specified at x is equals to 0 plus pv dx 0. Now at x is equals to 0, what is u? U is equals to 0, right? But if u is equals to 0, we know v is equals to 0. That means this term is gone because this fellow is equals to 0. The entire term is gone because this is 0. Now let's come to here. What is ae du by dx at x is equals to 1? This is equals to capital P. So that means I can rewrite it this one as dv by dx ae du tilde dx d capital plus v p minus small p of x v. Now we came to, this is also called as our weak form. Now we already know that our u tilde is equals to ni ui and du tilde dx is equals to dni dx ui. Then what is v? Because v is your best friend, which should be same as u, then with the same confidence I can write that v is equals to ni vi. Okay, and dv by dx is equals to dni by dx vi. So this is what I require to substitute back in here. And anyway, this will go and get substituted here. Now I am in a better shape. So I will rewrite it as minus integral dni by dx vi ae dnj dx uj, because they are dummy variables I can replace it i's by j's, plus, is it a plus or a minus? I made a small mistake here. This is a plus. V I N I capital P, and because here it is V, this is you have to write, but you need to know that this has to be evaluated at x is equals to L. Evaluated at x is equals to L plus small p Vi ni dx is equals to 0. Now let me rewrite it in a manner. I take everything out. Now I take Vi is common in this, Vi is common in this, Vi is common in this. So the main purpose of writing this in an integral in this form is to take out Vi out. Vi dni dx integral ae dnj dx dx uj. Because uj's are arbitrary constant, I can bring it outside. It is not a problem. They are not functions of x. Plus ni p evaluated at x is equals to L plus integral of p small p ni dx is equals to 0. Now we know that Vi's are not necessarily at all the places it will be equal to 0. So when can we have a stationary value of this function equals to 0 is the best thing is this equals to 0 is a trivial solution. But we don't want a trivial solution. We want a non-trivial solution. For non-trivial solution, this bracket fellow has to be equals to 0. So the bracket fellow means integral of, this is as good as saying that differentiating everything, if you call this one as pi as a potential, d pi by dvi, that's how you can remove v. So that is if you equate this dou pi by dou vi, since it's a linear in vi, this vi will go and everything equal. The best friend is there, while taking the presents this is getting vanished. This is where you see by differentiating with respect to vi or taking a non-trivial solution of this, you can write minus, or I will rewrite it with a plus, dni dx ae dnj dx dx uj is equals to ni p evaluated at x is equals to L plus integral of p ni dx. So this is nothing but F naughts, concentrated forces or point loads, and this is nothing but distributed loads. So this is integral. After integral I can write it in this manner. Okay. Now this fellow I can write it as Kij. Let's define what is Kij, Uj. Okay. So let me rewrite it in a simpler fashion. You can write it as ith component here, ith component, because I am writing for the ith equation. So or I can write it as k times u is equals to f naught plus f. Okay, or I will simply call it as f bar. So my k times u is equals to f. But what are u's? Let's take a two-noded bar. For two-noded bar, u is nothing but ua, ub, and f would be FA, FB. The values, you can get it by integrating this expression with respect to shape functions. So it's not a big difficult task. So let's define what is this one. So let's see that thing. For two noded bar, we know that NA of X is equals to 1 minus X by L or XLE, whatever you want to write it as. And NB of X is equals to X by LE. So if I take dNA by dx, that is equals to minus 1 by LE. Similarly, if I do dNB by dx, I'll get 1 by LE. Now I'm in a better position. Okay. Now I know these values to substitute back in these expressions to get my shape functions. So let me rewrite it. So minus 1 by LE plus 1 by LE AE, because these are rows, this is a column vector, and for the nj's it will be minus 1 by LE and plus 1 by LE integral 0 to LE dx is my K matrix. So let me multiply it first. 0 to L AE by LE square, it is 1 minus 1 minus 1 1 dx. Since this is independent of x, I can as well as write it as AE by L square 1 minus 1 minus 1 1 dx 0 to LE. If I integrate this, I'll get an LE, and that LE gets cancelled with respect to this. So my K matrix for a two noded element is given by AE by L 1 minus 1 minus 1 and 1. So this is the thing yesterday which I have used when I have given the example for you, and I said that I will define it at a later point. So this is the stiffness matrix for the two noded element. In brief, one can say that K is defined as integral of B transpose T B D some measure, right? So the easiest form to understand strain displacement matrix. The strain displacement matrix the strain displacement matrix is defined as the relation between epsilon and u. For example, if you look at our previous example where I started defining these things, here I already given you the relation between the the strain and the displacements. Here I can as well as write it as some B times U. Okay, so in our case epsilon is equals to du by dx. If it is tilde, this will also become tilde, but we know u is equals to these things, that is dni dx ui. That means I can write it as b times u. In our case b is defined as dna by dx and dnb by dx, where a and b are the nodes. Okay, so this is what, similarly this is for a two noded bar. For three noded bar it would be obviously dna by dx, dnb by dx, dnc by dx for three noded bar. I would ask you to go and review yourself for this definition. So that means our K matrix is defined as integral B transpose dB dx. This is constitutive law. So we know that sigma and epsilon are connected by E. So I can write this one as 0 to L B transpose E B. Actually this is an integration with respect to volume, but since we are only doing it, I removed A and kept it in this. So my D is equals to E in this case. My D matrix is just a simple Young's modulus in 1D bar. Okay, and A dx is my volume. I have to integrate with the volume since my area at a given cross section would be constant. If it is not constant also, it would also change it. You can integrate it with respect to thing. This will be a function of A, so it should not be a problem. So this would be the structure. So, and since our B transpose, just as I defined earlier, it is nothing but dNA dx dNB dx transpose, I'm bringing A here, AE dNA dNB dx dx. So that's what I have shown you earlier by taking this one as 0 to L minus 1 by LE 1 by LE transpose 1 minus 1 by LE 1 by LE give you on integration AE by L 1 minus 1 minus 1 and 1. So this is the K matrix or the stiffness matrix for one element in the these things. Okay. Similarly, I would ask you to first get the shape functions of n three noded bar, that is NA, NB, NC of x, and find dNA dx, dNB dx, and dNC dx. Once you define all these things, then you go back here. Instead of A and B, you will have A, B, and C. Here also A, B, and C, and you just multiply it. You will get stiffness matrix for a three noded element. That I will give you as an assignment yourself. You figure it out by integrating the stuff. That is not that simpler to integrate. You have to integrate each and every component individually after integrating this. In my case, it happened to be all are independent of x, so I did the integration outside. Okay, so now with this, the first part what I promised today is over. The second part what I said is I want to solve this problem. Let's have a bar and A. Let me redo it. Let's this be E and 2A. The cross section area is 2 times of this one, and this one is 3 times E. The modulus is higher, and the cross sectional area is A, that is half the times of this. Let's say this one is 2 times of E and cross section is 2A, and I have loaded at this end with a point force P. This is the problem I want to solve. Okay, in this case obviously I cannot put one noded element because I have a cross sectional changes. So the minimum discretization what I should do in this case is I'll consider it as a line element. This is one element, two element and three element. So this is element 1, element 2 and element 3 with a point load P. Its properties is E and 2A. This properties is 3E and A, and this properties is 2E and 2A. Now we know that K of an element is given by AE by L. Let's say the length of this element is L. This is 2L, and let's the length is 3L. I haven't drawn to the scale, but let's assume such kind of behavior because I want to keep it everything different. So we know this is of this form. But in the first case, for the K of the first element, for the first element, my A is 2 times of A. My E is, let me write it again neatly. For element 1, A is defined as 2A, E is defined as E, L is defined as L itself. So my K for the element 1 is given as just a minute. K is given as 2A E by L 1 minus 1 minus 1 1. For element 2, A is defined as A, E is defined as 3 times of E, L is defined by 2 times of L. So my K for the second element is given by A 3E divided by 2L 1 minus 1 minus 1 1. For element 3, my A is defined as 2A, E is defined as 2E, L is defined by 3L. So the K for the third element is defined as 2a 2e divided by 3l 1 minus 1 minus 1 1. But I am not interested in the element stiffness matrix of 1, 2 and 3. I'm interested at the global things. So let us see, go back, and we know the node number is, this is 1, this is node number 2, this is node number 3, this is node number 4. So the first element is between node 1 and node 2. The second element is between node 3 and node 2, while the third element is defined between the 3 and the 4, right? So let me write my kg, k global, k global stiffness matrix. A simple way to write is, first write the guiding things. This is degree of freedom u1, u2, u3, u4, u1, u2, u3, u4. Now similarly I can write here for guidance earlier, this is with u1, u2, this is u1, u2. Similarly the contribution here is, this is u2, this is u3, this is u2, u3. Here it is u3, u4, u3, u4. So if I look at this thing more closely, I know that one of the entry coming from this one u1 u1 is, let me take ae by l common, then it is u1 u1 is 2. Okay, for simplicity let me define all the three things. Okay, it's okay. So let me bring this thing here. So if you look at it, u1 u1 contribution, u1 u1 contribution is 2 times. Similarly u1 u2 contribution would be minus 2. u2 u1 contribution is minus 2, u2 u2 contribution is plus 2, because ae by l is taken it outside. So this is minus 2, because this is u1 u2, and u1 u2 would be minus 2, u2 u2 is plus 2. Done. Then I'll come here, if you look at here, u2 u2 is 3 by 2 al, u3 u2 is minus 3 by 2, and u2 u3 is minus 3 by 2, u3 u3 is plus 3 by 2. So this is this one is plus 3 by 2l with everything A by L is taken outside. Next, U3 is 3 by 2, and U3 is minus 3 by 2. U3 is minus 3 by 2. Okay, now let's see 3 and 4. Here 3 and 4 is 2 into 2, 4 by 3. So this is 4 by 3 minus 4 by 3 minus 4 by 3 and 4 by 3. So this comes as 3, and 3 contribution coming from the third element is plus 4 by 3. This one is minus 4 by 3, minus 4 by 3 and plus 4 by 3. This is what is called assembly. Now I'm done with the assembly. All the remaining terms are zeros. So let me add this up and let's rewrite it. So this is equal to AE by 6. Then this would be 6L. So this is 0, and this would be minus 12. This would be like this is 12 plus 9 will make it 21. This is, you multiply with 9, it will be minus 9, 0, 0, minus 9, and this is 9 plus 8, 17. This one is let me see there. Did I make anything wrong? This is 12. Is 12 plus 8. Okay, let me just 3, 9. This is 9. This is 12. 21. And this is 0, 0, minus plus 12. So if you look at this thing, all the diagonals are positive, and the top half is same as the bottom half, that is symmetric. Minus 12, 0, 0. That means if you go down and the same thing from the diagonal, minus 12, 0, 0. 21 minus 9, 0. 21 minus 9, 0. 21 minus 12, 21 minus 12, 12. So it is, let's see the properties of K. Properties of K. The properties of K are, first thing, diagonals are always positive. Second, K is symmetric. And there are other things, is one can show that if you have a structure, if I want to understand what is the meaning of if you are displacing a given node by unit distance, the amount of forces that are required at all the nodes to keep it under equilibrium is given by the structure. So that means in the first case, if I move it by a unit distance in this direction, I need to put a 12 kilonewton in this direction, 12 kilonewton in that direction, 0 at here, 0 at here. So that's the reason one is 12, another is minus 12, 0 and 0. So that is what a column vector of A of the K matrix, or let me write it in this manner, ith column of the K matrix is if a unit displacement is given at ith node and at all other nodes displacement is kept 0, the forces are the equilibrium forces that are required to sustain this motion is given by the vector. So if the displacements are 1, that means this is the ith column. This is F0, F1, F2, F3, F4, so on like this. Some forces are there, so on, Fn are there, and all are 0 except my U I is equals to 1 and all others are 0. Then I will get equilibrium forces F1 because of I, F2 because of I is equals to 1, so on, Fi, I, so on, Fn, I. So this means it's the same thing as what I described in the above things. So these are nothing but the equilibrium forces. Each column represents an equilibrium forces that are required, provided at the ith node a unit displacement is given and all other places the displacement is kept 0. So in an alternate way of saying is, here EA du by dx du dx is equals to 0 is equilibrium equation. In the same manner, K times is also same equilibrium, but it is in discretized form. So this is also an equilibrium. As I explained to you earlier, Kx is equals to F for spring. Any structure is a kind of spring like a structure. So What we are saying is Ku is equals to F, what we obtained out of all this finite element formulation represents conditions. The same equilibrium as what we have seen earlier, but it is in the discretized form. And hence, this equilibrium is a static equilibrium. This equilibrium is, uh, the, yeah. So one thing we need to understand is, as I said, there is another property, which thing is fourth one, K is singular, K global. Global stiffness matrix is singular matrix. That means it is not invertible. Why it is not invertible? Because the structure is not statically stable. That means if you take the structure, if you move the structure as it is by the same amount, it is a rigid body motion. That is, FEM cannot resolve a rigid body translation, rigid body motion. In this case, for it is, since it is 1D, it is purely a rigid body translation. So if you translate a structure by 1 mm, or if you translate by n some x amount of mm, both things gives you no strain. So finite element cannot define you these kind of things because it cannot differentiate one rigid body motion from another, because there are infinite combinations of rigid body motions. So all these infinite rigid body motions cannot be captured. That's the reason K is singular. Like in the previous class, after substitution of BC, or if the structure is statically stable, then K is invertible. So let us see, for this thing, let us see how to handle the boundary condition. How to handle the boundary conditions. So for that, let's come back to our own problem. So for the own problem, this is 2A and E, 3E and A, this is 2E, 2A with a point load capital P. We know that U is equals to 0 when X is equals to 0. So, and du by dx, this length is L, this length is 2L, this length is 3L. So from here, if I am measuring X, my global X will give you 6L. So du by dx at 6L corresponding to this beam, which is 2E, 2A at this thing, is equals to capital P. So this is our boundary conditions. So let us see how the boundary conditions can be mentioned. So let us see. First, let's write the force vector. So since there are no concentrated forces, the concentrated forces are all zeros. Sorry, since there are no distributed forces, no distributed forces, so everything is 0. There are 4 nodes, so we need to make 4 zeros. So at the node, nothing is there. Now things that are coming from the concentrated force. At node 1 there is nothing, at node 2 there is nothing, at node 3 there is nothing, at node 4 there is so this is due to concentrated or point forces. Okay, this is fine. Now let us get back to how to substitute the boundary conditions. So let's take this thing AE by 6L 12 minus 12 0 0 minus 12 21 minus 9 0 U1 U2 U3 U4 is equals to F naughts are only 0 0 p and F is all 0, so I can write it as total F is equals to 0 0 capital P. So now I already know my U1, this fellow and that fellow. So my KUU will be AE by 6L 21 minus 9 minus 9 21 12 0 minus 12 and 12. So this times U2 U3 U4 is equals to 0 0. So I need to eliminate entire thing. So now if you can go back and check that this guy is invertible, so you try to inverse it with the corresponding thing, then you can determine your u1 u2 and u3s. Let me just do it for you. Let's assume p is equals to 1, capital P is equals to 1, then I will just make this fellow as we will get our solution back. So meanwhile, if you have any questions, I can entertain it. Sorry. Hello. Can you hear me? Okay. So let us again review it from this place. So there are no distributed forces, so F is equals to 0, and concentrated forces are only 0, 0, 0, and P. So this is the kind of things. Then this is our global stiffness matrix, and this is our all degrees of freedom. But we already know, substituting the displacement boundary condition, that u1 is equals to 0, that means I will eliminate my entire row and the column. So my KUU is given by this small thing, that is 21 minus 90 minus 9021, these kind of things, and my unknowns are u2, u3, u4, and my FU is 0, 0p. Once I invert this using the MATLAB here, which I define, and assuming P is equals to 1 and A is equals to 1, I can define my U1, U2, U3 in this manner, and my solution is U2, U3 is 1 half, 7 by 6 and 7 by 6. These are the three things. Now, we know that our NA and B is given by like this. So UB is equals to 1 half, UB is 1 half, and this is X by L. So this is given by element 1 is given by X by 2L is U tilde for the element 1. Now for the element 2, U tilde of X is equals to UANA plus UBNB, which is A is node 2, B is node 3, and NA is 1 by XE by LE, but the length of the second element is 2, because LE is equals to L here, LE is equals to 2L here, so I will have 1 minus X by 2L and X by, so sorry, this is XE by 2L, but we know that in this case XE is equals to X minus L. So if you want to write it in a global coordinate system, then you can write it as U2 1 minus X minus L divided by 2L plus U3 X minus L by 2L, but my U2 is equals to 1 half, U3 is equals to 7 by 6, so 1 by 2, so 2L minus L, so L minus X by 2L plus 7 by 6 X minus L by 2L. So you can simplify it further. So if you don't like, you can simplify it. So this will become 1 by 12L. This will become 3 minus, so minus 4L, and this is minus 3x, this plus 3x, this will become 4x. So this is equals to X minus L by 3L is the U tilde for the second element. Similarly, for the third element, LE is equals to 3L, and U tilde of the third X is UANA is 3, NA is 1 minus XE by LE plus U4 XE by LE. So here U3 is 7 by 6, 1 minus XE is equals to X minus 3L. So X minus 3L by 3L plus 7 by 6 x minus 3l by 3l. That will give you, let's take 7 by 18l. So if you take this one, this is 3l, this is x, and this will give you x minus, this is minus x, this is plus 2, this is 2x. So anyway, let's write it as 3l minus x plus 3l plus x minus 3l. So that will make your this x and that thing is gone, this is gone. So this will give you 7 by 6. So is independent of x. So that means I can summarize that to summary, u tilde of x for the element 1 is equals to x by 2l, and x lies between 0 to l, and u tilde for the second element is given by x minus l by, for x lies between 3l to l, and u tilde 3 of x is equals to 7 by 6, x lies between 3l to 6l. So now you have solution for the all the three. So for the first one, it is x by 2l is the solution. This is up to l, this is up to 3l, and let's say this is up to 6l. From so this is another line, and the third one is a constant 7 by 6. So in this manner, we have solved this problem completely. And once you know these things, you can obtain the strains, then you can obtain the stresses and other things using post-processing. Because now you know you can also obtain epsilon tilde is du dx, and your sigma is E times epsilon. In this manner, since you know U completely defined, you can get your strain, and since you know the strain, you multiply with the Young's modulus, you can get these things. With this, we'll complete today's lecture, where in today's lecture what we did was we tried to look at P convergence, and then we tried to show how to get the stiffness matrix for a bar element, and using the stiffness matrix of a bar element, we tried to solve a problem, 1D problem, and obtain the solution which has 3 elements with 2 noded, 2 nodes per each element. And then we got our solution and presented it. With this class, the chapter 2 is over. In the next class, I will make use of the same solution which I obtained in the today's class to solve the problems for the trusses. So in the next class onwards, even though it is a 1D formulation, we will try to solve some 2D problems. 2D problems are truss-like structures, and after the trusses are over, in the third chapter, we'll also deal with the beams. So at this point, the class is over. I would happy to take few questions if you have anything.